Okay, so right, so what I said was we went through and got that solution, but now we want to maybe go through an example that's slightly more complicated because we were really lucky in the last example, or I guess not lucky, but intentional, right? We said this boundary condition over here at t equals 0, or at x equals 0 is 0, temperature is 0. And over here, this boundary condition was q dot equals 0. Well, that's homogeneous in the x direction, which is what's necessary for superposition. But where are you ever going to find a problem where temperature is 0 on one side and it's adiabatic on the other, right? It's a really pathological case. And so we want to actually make this a little bit more realistic, and I'll show you how to go through the steps to solve it. So first, what we're going to do is we're going to look at this problem, right? So here's our problem on the left. This is what we did last time. Today, what we're going to start with is this problem on the right. So now we have, note instead of T0, we have T infinity. On the right-hand side, we have a convection condition. We have flux on the bottom and temperature on the top, right? And none of those things are 0. So what we want to do is let's go through and solve this problem using 2D separation of variables. And I'll show you two techniques that we can use to deal with the non-homogeneous boundary conditions in the different directions. The first one's pretty straightforward. It's just using transforms to get a homogeneous problem in one direction. And then the other one is actually just kind of a long-winded way of doing the problem. You just break it up into two problems that are homogeneous and solve them both, and then add them together. Okay, so let's start with the kind of more straightforward one. So like I said, in this example, we have these boundary conditions. If you look, none of these directions are homogeneous. We have something going on in all of the directions. So our challenge is, let's get this to be a homogeneous problem in one direction and then solve it. We're going to start by writing out the boundary conditions for all of these things. First, let's write out the PDE. So the PDE for this problem, so the PDE is the same as it was before. Where we end up being different is looking at the boundaries. So let's write out our boundary conditions. So our first boundary condition, let's look at x equals 0. We have t is equal to t infinity. Okay. At x equals w, we have, let's maybe help ourselves a little. We have let's draw a control surface here, right, on the boundary. So right on the boundary at x equals w, what do we have, say, going into this control surface? We have conduction. Okay, so going into that control surface, I have conduction minus k, partial of t with respect to x, evaluated at x equals w is equal to what? And what's happening on the right side? Again, let's draw this. Be careful how we draw our arrows here. So we have something coming into the surface on one side. Just a few atoms to the right, we have something else happening. That's convection. So on the right-hand side, we have h bar times what's the temperature at x equals w, T at x equals w, minus the convection temperature to the surroundings, right? And note, neither of these are homogeneous so far, right? Okay, so that's the x direction. Let's do the y direction. In y direction, what's going on at y equals 0? Again, we can sit here and draw a little control surface. Okay, so coming into that control surface, we have q dot, which is a specified heat flux, q dot double prime. And it's going, I guess we're drawing this in the positive y direction, so it's a positive q dot. And then what's leaving? That's conduction into the body. What's leaving that surface? So that becomes minus k partial of t with respect to y at y equals 0. Again, not a homogeneous boundary condition. Right? Okay, last boundary condition. This one's easy. T at y equals h is equal to th, not homogeneous. Let's find a way to get this to be a homogeneous problem. So what's one thing that we could do? Well, we could define a new variable, and let's call that variable theta. let's say we're going to define theta. And let's make that variable something convenient so that what comes on the right-hand side of some of these boundary conditions ends up being 0. So we could say that theta is equal to the temperature T minus T infinity. Okay. So if we note, right, we're still saying that theta is a function of X and Y because T is a function of X and Y. But it's relative to this T infinity here, that is a constant. Okay, so if we make that substitution, the PDE becomes, substitute theta in for T, and you take the second derivative or second partial of that constant, that goes away, so it just becomes partial squared of theta with respect to X plus partial squared of theta with respect to Y is equal to 0. Now we have this PD in terms of theta, our new variable. Our first boundary condition, see if I can kind of scroll back and forth. So our first was T at X equals 0 is equal to T infinity. Okay, so this becomes theta at X equals 0 is equal to 0. Right? So we're taking now this problem with respect to, or with reference to T infinity. So if we're forcing that to be T infinity at that boundary condition, then it's 0, right? So now we just created a homogeneous boundary condition at X equals 0. Okay, 2, the second boundary condition was at X equals W. So this becomes minus K times the partial of theta with respect to X, evaluated at X equals W is equal to H times T at X equals W minus T infinity. So we substitute in theta, and we just have now theta evaluated at X equals W times H bar. Okay, this is now homogeneous, right? D theta dx is a function of theta, and what's on the right-hand side is also a function of theta. So there's nothing left over that's not directly related or multiplying theta. Okay, so through this transform, we've just created a homogeneous situation in the X direction. Right, that's really all we need to solve it. So we can continue on, but let's actually just finish with our little transform here. So then in the Y direction, the flux in at the bottom becomes Q dot double prime is equal to minus K times partial of theta with respect to Y, evaluated at Y equals 0. Okay, and then for theta at Y equals H is equal to TH minus T infinity. Okay, so Y is definitely not homogeneous. We still have Q dot on one side and we have TH minus T infinity, but like I said, this is now a problem that we can actually solve using separation of variables. So now we have our mathematical statement of the problem in terms of theta, right? And the next thing is we can then proceed with separation of variables as we've done before, as we did last time. So I did that already for you on this page. I didn't want to make us sit here and write it all out, but let's just kind of walk through it. Okay, so we say now here, theta is a function of X and Y. So we're going to make the assumption, because we satisfied all the conditions, that we have homogeneous boundary conditions in one direction. The problem is linear. The domain is simple, right? All those assumptions that we had to make, if we satisfy those conditions, we can then make the assumption that we can separate this into a function of X and a function of Y separately and then solve for them independently, right? We went over that last time. So, okay, we say we've got this function of X and this function of Y. And then we're going to substitute this assumption into our equation here. And we end up with, right, the partial with respect to X on one term, the partial with respect to Y on the other term. And then we say the partial derivative with respect to X means that Y can come out here. The partial derivative with respect to Y means that X can come out here. And we divide everything by theta X times theta Y. Okay, and then that gives us the thing down in the left-hand corner. And then we end up with what's in the right upper right here, which is we've now separated this equation into a function of X and a function of Y. Right? We follow that. Exactly the same thing we did last time. Nothing has changed except for now we're calling this theta instead of t. Okay. All right, and then we say that these both, in order for this equation to be true, these things both have to be equal to a constant. Remember why that was? It's because if I change something here, the only way that I could change something here and this still remains true is if both of them are equal to a constant. So then we call that constant lambda or lambda squared in order to indicate that it's definitely a positive number, that lambda. And then we have d theta x is either minus or plus lambda squared theta x. D theta y squared is either plus or minus lambda squared y squared. And then we have to make sure to pick the sign according to whether it's a homogeneous direction or not. Right. And remember, now you've been through this process, so you can probably see why we did this now. We have to pick the sign on the homogeneous direction such that we get the periodic function that lets us get the eigenvalues to solve in that direction. And then the other side, just the non-homogeneous side, kind of comes along for the ride. Okay. So to get the periodic function, which is sines and cosines for this type of problem, we pick the positive in the homogeneous direction, which was x. Right? Again, we could have homogenized in y had we had the right conditions there, but we did it for x. So this becomes our eigen problem here. Right? This is the ODE that we're trying to solve in the x direction to get our eigenvalues. Okay, we went through that kind of quickly, but hopefully that everybody's following.